we were going to get from this right here, A, B, and C. However, we have to be at the point that we're talking about. This gives you the normal vector at any given point. You have to provide the u and the v. So what's u and what's v to get me to that point? See, I have to be on this point, right? What u and what v get you to that point? And where am I looking to determine this? The original surface, right? The question is, what u and what v do I plug in here to get me root 2 over 2, 0, root 2 over 2? So what's pi over 4? U, how are you determining that u is pi over 4? So this one right here, this z component is the only one that has just one variable in it, right? And so if you need that to match this, then what you can say, I'm going to erase this and keep that there. What you can say is that cosine of u must be equal to root 2 over 2. And now remember, u is between 0 and pi. Cosine is the x-coordinate on the unit circle. Where's the x-coordinate root 2 over 2? At pi over 4. So that's the only place that that's going to happen. U has to be pi over 4. Okay, so I've locked down one of the variables. Now let's go try and get the other one. If I take this right now and I plug in pi over 4 for u, and I don't know what v is yet, right? Then I'm going to get what? Sine of pi over 4, which is root 2 over 2. Cosine of v, I don't know. And then sine of u, which is root 2 over 2. Sine of v. And then cosine of pi over 4, which we know is root 2 over 2. Right? That's where I would be right now. I need to figure out what the v is. So you need to get, what do you need to get? You need this right here to turn out to be that, right? Which means this has to be 1. And then you need this to be 0, which means this has to be 0. So simultaneously, you need cosine of v to be equal to 1, and you need sine of v to be equal to 0. And
but you need to be careful with because what if that was negative? Then
what's negative?
If your x-coordinate was negative,
Then you wouldn't be here.
yeah, so you would need a pi, right? So that cosine could be negative.
Why do you want it negative? I'm not following why you want it
What I'm
negative.
saying is you would need to be careful with the signs. You need to watch out for those on the coordinates. I'll explain it after class.
Okay. There's only one place where cosine can be 1. It's going to be at 0 or at 2 pi. But we can say 0 here because on the spherical, we don't go all the way over and overlap your same point. But you would be at the same place anyway. The point's the same. So v has to be 0 here. Cosine of 0 is 1. Sine of 0 is 0. So v is 0. Now, because of that, I can come down to the cross product. So at u is pi over 4, and v is 0. This is u, this is v. U is pi over 4 and v is 0. Then the cross product becomes what vector here? So what is sine of pi over 4? Root 2 over 2 and square it. 1/2. Times cosine of 0 is 1. So this is just going to be 1/2, isn't it? And then this one doesn't matter because what's sine of 0? 0, so that's 0. And then look at the last one here. What's sine of pi over 4? Cosine of pi over 4. Root 2 over 2 again. Root 2 over 2, root 2 over 2, you get 1/2 again. That's your normal vector. So final answer. Any questions up to this point? Final answer, coming back to this, A for us is 1/2. X minus root 2 over 2. plus b, which is 0, kills off completely your y part of this plane equation. And then c, which is 1/2. And then z minus root 2 over 2 equals 0. That is the plane equation. If you sketch that plane, you will be touching this point, and you will be tangent to that sphere. Hey, same problem. Let's think about this for a second. What would the north pole of this sphere be? What point would it be? What would the north pole be? 0, 0, 1, right? Okay, 0, 0, 1 would be the north pole. What would the equation of the tangent plane be there? The xy plane moved up 1. Z is 1, right? Would be the equation. Let's just look how we would get that, okay? Go into here. Well, we need to figure out what the u and the v is, but that would be easy because think about this. To be up there, what would you'd be, phi would be 0, right? Phi would be 0. What would happen if phi is 0? Phi is the same as which variable here? U. So what would happen at phi is 0 here? Or u is 0. That's 0? 0.
0. Sine of 0.
Sine of 0? No, this is 0. 0, 0, 0? Hold on. Something ain't right here. Hold on. This should work. To be at, oh wait, no, we need this to be 1. Hold on. What would phi have to be?
2 pi.
Yeah, cosine of 0. Cosine of 0 is 1. What am I not getting on this? All those are 0, right?
The sign in the middle term on the cross product is supposed to be negative.
I think so too.
Where?
The cross product,
This?
or you plus RB.
That wouldn't change this at all, though, right? I mean, we can talk about that after class, though. I don't think it's wrong, but we can address that later. Why are we not getting this? 0, 0, 1 is on this sphere. This is where I start to worry because math should not fall apart like this. There's something wrong. Pi 0. V is independent, completely independent. What should our vector be here? Our normal vector should be what? Straight up, right? Which should be 0, 0, 1, right? Let me just double check that cross product is right. Do you understand my concern here? Okay. I just thought it would be a cool visual thing, like we could all make sense out of it. Oh, okay, yeah, North Pole here. We should just have a flat sheet here. That should be z equals 1. So we should be able to recover that equation very quickly from this, but for some reason, we are not recovering it. Sine, cosine v. Theta. What about theta? V. V can be anything, can't it? Because doesn't matter what this is. I'm going to be at the u is 0, so I should be straight up. And then turning doesn't matter anymore. Walk out 1.
Would v be 0?
Well, V could be anything. But it doesn't matter because look at in here. Right? In here you're going to get 0, 0, and then again 0. So if your normal vector is the vector 0, 0, 0, it kills everything off, right? I'm going to have to leave this as an open one. I believe the math is okay. Like, I believe that there's a mistake I'm making more than the math is wrong. So let's leave it as an open question because I don't want to eat up the rest of the time that we need. That's going to bother me for the rest of the day, though. Okay. I'll figure it out after class. But I still, no, this is very troubling. I'm hoping it's just one of those Monday problems where I'm like, oh, well, yeah. But I don't see what I'm doing wrong there. Vectors, the 0 vector. Okay, let's move on. Okay, surface area. We were just talking tangent planes. Now we talk surface area. This is actually pretty amazing, this formula right here. But I'll show you the picture for it, but let's just look at the formula real quick. Let's say you have a surface that you can draw using your vector function, and you've got your restrictions set on u and v. So you draw a surface, right? If you want to know the surface area of that surface, all you have to do is the double integral over d of the magnitude of the cross product of the partial derivatives dA. What? Okay, so here's what's going on. Let's go back to this sphere. Okay? And if I pick some arbitrary point on that sphere, I've got those two tangent vectors, right? Like RU, RV, right? Those are my two tangent vectors. Now, do you remember what the magnitude of the cross product of two vectors is? Yeah. It's the area of the parallelogram spanned by the two vectors. So if you give me a vector u and you give me a vector v, and then imagine the parallelogram formed by those two, the area of that is the magnitude of u cross v. That we learned way back when we were talking about cross products.
So the integral is just the sum of all those cross products?
Yes, but there is something subtle here we have to remember. This vector could be very long, right? And this vector could be very long. Really, the vectors are there to give us direction. We need to scale those vectors back by an infinitesimal. In other words, we need to look at this little tiny infinitesimal patch on top of this surface. So I have here go small. I don't know what that means. Okay, so here's what the vectors may look like, right? The vectors might be really long. But we want just that little red patch, so what we do is we scale it back. And to do that, we scale by the differential du dv here. So that's what we did when we were talking about tangent vectors before on curves, and we were trying to do this arc length. We scaled back the vector by using the differential, but then we used ds. We used the arc length differential. Here we're going to just scale by the differential of u and differential of v. So remember, these are like numbers. Small numbers in front of a vector should shorten it, right? So we're really doing du times the vector r, partial of r with respect to u crossed, with dv, and then partial of r with respect to v, and then we're taking the magnitude. And what winds up happening, properties of cross products, is that you can pull out, this is properties of cross products, you can pull out the du dv because they're scalars, they can come out of the cross product like this. And so what you get here is this right here times that, but that right there is dA. if you go back and look at the UV plane, which is where your variables are coming from, then du dv is just this infinitesimal little square, and that has an area to it. So we're doing the magnitude of the cross product of the partials with respect to area. And that's where the formula comes from. Okay? So we're going to do something really cool right now. It might make up for whatever the heck just happened. I'm still not happy about that. I want us to find the surface area of not the unit sphere, that's too boring, of the sphere radius r. In other words, I'd like for us to actually come up with the formula that you would see in the back of a book for the surface area of the sphere. Does anyone know what it is? You're thinking volume. Surface area is not one that most people know off the top. So let's not look it up. Let's come up with it on our own, okay? All right. First, let's draw the sphere. So to draw the sphere R of uv, it will be r cosine. So let's use the same thing we had before, okay? There we go. Cosine, I did it the other direction, didn't I? I did sine u cosine, cosine v, sine u, sine v, cosine. I forgot my r here. Oops. R sine u sine v, and then r cosine u. U is between 0 and pi, and v is between 0 and 2 pi. Now the r there is like the rho was back in spherical coordinates, right? That number in front dictates the radius of the sphere. Are y'all okay with that? Okay, so we need to take this. We need to take the cross product of the partials, right? Cross product of the partials, take its magnitude. Okay, quickly. What is the partial of r with respect to u? R cosine u. Cosine v? R cosine u sine v, and r negative r sine u, right? And then the partial of r with respect to v is negative r sine u sine v, and then r sine u cosine v, and then what? 0. And now let's cross them. Ru crossed Rv will be a vector. So we cover this one up. This times this is 0 minus this, but it's going to be plus, so what? R squared sine squared u cosine v. Okay, I forgot the squared, r squared. And let's go through this one again because you were saying that I might have been off by a sign on that one. Okay, so if we're going to do the middle one, we're supposed to do this times this, 0, minus, right, this times this. So these are both negative, so that would be positive. But we were supposed to subtract it, right? In the formula, it's this times this minus this times this, but then negative because it's the middle component. So what would that be? R squared sine squared u sine v. Yes? What's next? Last one. So this, r squared sine u cosine u cosine squared v minus, yeah, it would be minus, but then plus, wouldn't it? Okay, r squared sine u cosine u sine squared v. And that we could do Pythagorean on. When we do Pythagorean on this, this would really turn into r squared sine u cosine cosine u. We all right with that? Okay, I need the magnitude of this. What is the magnitude of this vector? So how do we find magnitudes of vectors? Square root of the sum of the squares of the components. So I square this right here. I get r to the fourth sine to the fourth u cosine squared v plus, now I square this one. R to the fourth sine to the fourth u sine squared v plus, now I square this one. R to the fourth sine squared u cosine squared u. You all still in business here with me? All right, what can I do here? I can pull out r to the fourth from all of these, right? And then I can take the square root of r to the fourth, which would just be r squared on the outside. So r squared on the outside, square root of, now on these first two terms right here, and remember the r squareds are gone, right? Or r to the fourths are gone. I'm not looking at those anymore. On the first two, what can I pull out? Sine to the fourth? Sine to the fourth u. And what would I be left with if I pulled out sine to the fourth from here and here? Cosine squared v plus sine squared v, which is just 1. So that's just that, isn't it? These two are just that. Then what? Plus sine squared u cosine squared u. And what could I pull out of that? Sine squared. And when I pull out sine squared u, from here and from here, I'm left with, I'll go ahead and write it, sine squared u plus cosine squared u, which is 1 again. Yeah? Y'all with me? So then you just get r squared square root of sine squared, but that's just r squared sine u. The reason why you don't have to do absolute values because u is restricted between 0 and pi, right? And because of that, sine is always positive there, so you don't have to worry about it. So we're good. That's the magnitude of the cross product. What are we supposed to do with that? Do the double integral. So now I'm supposed to do the double integral over d of the magnitude of the cross product with respect to area. Here, our domain I gave earlier was u is between, what's u between? 0 to pi, and v was between 0 and 2 pi. And what am I integrating? R squared sine u d. Well, in this case, I'm going to have to do d v du, unless I want to switch the order here. Understand what I'm doing? Let's switch the order. Let's just switch it. Let's do 2 pi here, 0 to pi there. Let's change this to u. Am I allowed to switch the order? Because they're both constants, right?
Yes.
So I can do this. Okay. What is the antiderivative of sine u with respect to u? Negative cosine. So I get 0 to 2 pi. Here comes, I've got, what about the r squared? It's a constant. Let's pull that out. R squared. Okay. Negative cosine u evaluated from u equals 0 to pi. And then after I'm done with that, dv. What happens when you plug pi in? You get negative, negative 1, right? Negative, negative 1, which would be 1. What happens when you plug in 0? You get 1, so you get minus 1, but you're subtracting that.
So
2. So this right here is 2. Yeah? R squared integral 0 to 2 pi, and we're integrating the constant 2 dv. The 2 could also come out, but really doesn't matter at this point. What's the antiderivative of 2 with respect to v? 2v. So let me write it this way. 2r squared v, and I'm evaluating from 0 to 2 pi. So what do you get if you plug in 2 pi? Get 4 pi r squared, and if you plug in 0? 0. Okay, so if you look this up, the surface area of a sphere of radius r is 4 pi r squared. I hope.
sounds like we have
Y'all can Google it. Someone can Google it real quick. I'm pretty sure that's what it is, but. I've got to get through one more example. I've got 15 minutes. It is 4 pi r squared. Okay. Surface area. That's pretty cool, huh? All right, now, there are some very special circumstances that could lead to some easier computations. As you just saw, the magnitude of the cross product can be a little bit messy, right? So if you have a very special scenario, and this will happen quite a bit in the next few sections, where your surface is actually a function of x and y. So you remember when we were talking about surfaces in the very beginning? We said z is a function of x and y, and it drew this sheet hanging up in the wind, and then we could find the volume under this. But that sheet up in the wind was a function of x and y. The sphere we just had is not a function of x and y, so we do not have that case. But if we do have this, that means that x is just whatever x wants to be, and y is whatever y wants to be. See, x and y don't depend on each other. And the z depends on both the x and the y. Then, when you take the magnitude of the cross product, this is what it becomes. So let me show you what I'm trying to say. If I just say, look, we have the standard r of uv, right? And then we have these 3 components. And this can be any mixture of u's and v's here, u's and v's here, and u's and v's here, right? That's the general scenario. But if we say that u is x and v is y, then we write r of x, y equals, and here's the big thing. If x is just x, in other words, if u is just u, okay, and y is just y, or in other words, v is just v, and this z is just a function of these two, then this right here is a function of u and v. Right, so we're switching from uv over to xy because this is stuff we did in the past. As long as this is the only one that mixes up the x's and y's, and these two are just x and y. Not sine x, not x squared, x, y, function of xy. If that's the case, then that magnitude of the cross product, all that stuff, simplifies to be this. And then I put y. So let's just see real quick. What would the partial of this r with respect to x be? Which would be the same as the partial of this with respect to u. So what would that partial be? 1, 0, and then whatever derivative of f is with respect to x, right? Okay, and then what would the partial with respect to y be? 0, 1, and then whatever the partial of f with respect to y would be, right? Now, if I cross this, look what happens. When I do my first part, what do I get? This minus this. So I get negative. So I'm put cross here because I'm lazy. Cross, you would get negative partial of f with respect to x. What would the next component be? So you cover this up. This, then change the sign, and you get negative partial f with respect to y. And then what would your last component be? 1, 0, so just 1. right? That's what it would be every time. If it looked like this, every time it would be this. What's the magnitude of this? This squared plus this squared plus this squared, right? Square root, that's what we're saying, okay? So you don't, if you memorize the formula, you actually don't have to do the cross product and do the magnitude. You just apply the formula. Understand? Only happens if your surface is a function of x and y. Question?
Yes, like you said, X can't be.
That's right. X can't be a function. Good old no, not constants, but good old-fashioned surfaces where your domain is the ground and your surface lives above it. Z is a function of x and y. So look, this is a really cool problem visually, and it seems like it'd be very difficult to answer this question. Find the surface area of the paraboloid z equals y squared minus x squared, which lies between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 9. Okay, surface area, okay, paraboloid, all right? We've got this paraboloid. It looks like if x is 0, it looks like a parabola that opens up, or opens out the, y, as y gets bigger, z gets bigger, positive. But if y is 0, you get negative. So it's kind of like the surface that goes like this, but then like that. Huh? Like a saddle. Okay, you want to know the surface area of that, but only between these two cylinders. These two cylinders open up which way? The z-axis, right? So it's kind of like you got this weird shaped paraboloid. I'm going to do a terrible job. There's my paraboloid, and I'm cutting through with a cylinder and then a smaller cylinder, and it's where those cylinders hit that surface. I want to know the surface area of that. I mean that. What's its surface area? Understand? You see that? Now without the picture, that's kind of mess, you would be hard to see that. But see, from the top, right, you have the cylinders popping through that surface. Just that. Okay. First of all, the surface we're trying to find the surface area of. Is it a function? Can you write it as a function of x and y?
Yes.
Absolutely. Here it is, right? So this is some function of x and y. So that means the double integral over the region D of r partial of r with respect to u cross partial of r with respect to v dA can really be turned into double integral over D of square root of, what did we say? 1 plus partial with respect to x squared plus partial with respect to y squared. And the negative parts that we had before, because it's squared, doesn't matter, right? That's dA. This is the special case. We have it. So what is the partial of f with respect to x? Negative 2x. What's the partial of f with respect to y? 2y. Okay, let's go back over to this integral. Double integral over d of square root of 1 plus 4x squared. That's what happens when you square negative 2x. And then square 2y, you get 4y squared dA. All right, this is our double integral, okay? Now we need to figure out, we're dealing with x's and y's, and we need to figure out the region that we're going to do this integration over. Yes, because the region, remember the two cylinders popped through? That region on the ground looked like this. If this is x and this is y, on the ground it looked like cylinder radius 1, cylinder radius 3. This was our region on the ground, D. D is perfectly suited for polar. So we're going to take this double integral over x and y in Cartesian, and we're going to turn it into a double integral over polar. Isn't this fun? So this becomes, let's see, double integral. What is my polar region, by the way? We should probably get that. We got theta and r restrictions, right? R's from 1 to 3. 0 to pi, good. Okay. Now, it doesn't matter which one I do first because they're both constants. So I'll do 0 to pi out here. I'll do 1 to 3 out here. And then square root of, now this looks bad initially. Look, yeah, pull a 4 out of these two. And you get x squared plus y squared, which is r squared by definition when you do polar, right? So this is just square root of 1 plus 4r squared r yr. Because we went to polar, r d theta. And boy, that r is actually pretty convenient now, isn't it? Because this will be a basic u sub. Let me see if I actually worked this one out. I did not work this one out. I think you could take it from there, right? It's a basic u sub. Okay. With time to spare. Let me give you the homework assignment for this. I want to go back to the note because I went through this pretty quick without actually being clear on the formula. We said that if the surface is a function of x and y, then the cross product becomes this, right? But I never actually scrolled down and said, therefore, the surface area is the double integral over that thing, right? dA, right? But I did that when I did the example. Okay, there's the homework. There's a bonus question in here to be turned in at the final exam if you're interested. So on these homework problems, you're going to be finding surface areas where you're going to have to mechanically do partial of r with respect to u, partial of r with respect to v, cross product, magnitude, like work through it. And then there will be other problems where it's the special case where you just go a little shorter. So I hope that goes okay. All right, you're free to go. I'm going to sit here and see if I can figure out what the heck was wrong with that problem earlier.